I want to welcome you to this particular channel again, where we produce content on topics relating to chemistry, biochemistry, and various other subjects. In this particular video, I'll be talking about how to calculate pH for different kind of solution, whether it is a basic solution, whether it is an acidic solution, or even when you have a buffer system. So I'm going to be giving you a summary on how to go about questions involving these different kinds of solution. But basically, to start with, there are some things that you have to know about. The first thing to know is about the two major ions, which I'm going to be mentioning frequently in this particular video, which is the hydrogen ion and the hydroxyl ion. So one is positively charged while the other is negatively charged. These ions are what we measure in solutions to determine the pH of that particular solution. So the amount of this ion in a particular volume of solution, which is the concentration of hydrogen ion in a solution, that we use in determining the pH of that particular solution. For this particular topic, majorly we represent the concentration of the hydrogen ion as this. So anywhere you see something like this, it means we are talking about the concentration of the hydrogen ion, which is the number of moles of the hydrogen ion in a particular volume of solution. So in a way, you can say that if you know the number of moles of the hydrogen ion over the volume of your solution, that will give you the concentration of the hydrogen ion. Now you can also have the concentration of this OH minus, which can also be represented as this. So this represents the concentration of the hydroxy ion, which is usually in mole per dl cube, or you can say the concentration is in molarity. So these are the basic things that you have to know, because I'm going to be mentioning those two things frequently in this particular video. And like I said, the concentration of the hydrogen ion or even the hydroxy ion can be used to determine the pH of a particular solution. Now, we have different kinds of solutions. Like I said, a solution can be basic, it can be acidic. At the same time, you can even have what we call a buffer system. In this particular video, the calculation of pH would be focused on an aqueous system, that is a solution whose solvent is particularly water. Now, solutions involving water as solvent usually contains hydrogen ion, because water in itself can self-dissociate. That is, water can dissociate to give this H plus at the same time to give OH minus. At the same time, in any aqueous solution that you can have substance that can produce more hydrogen ion in addition to the one that you have normally in water itself. At the same time, you can also have substance in a solution that can take up H plus that can remove H plus from the solution. So substance that produces more H plus in an aqueous system are what we call acid. So acids produce H plus in an aqueous solution. They produce H plus, while base remove H plus from a solution. So these two kind of substance, one will produce H plus, while one will do what? Will remove H plus from a solution. So if you add an acid to an aqueous system, what happens is that the acid will dissociate to give us more H plus, while if you have a base in a solution, it would remove H plus from the solution. So, and that in a way will also affect the concentration of H plus, particularly when you are trying to calculate your pH. If you have a solution that contains a base, or if you have an aqueous solution that contains a base, you will expect that the amount of H plus in that particular system will reduce, because the base will remove H plus from the solution. But when you add an acid into a solution, what happens is that acid produces more H plus, and that means that the concentration of H plus in that solution will increase, and that will certainly also affect the pH. But generally, pH is just like a way of measuring the amount of H plus, or let me say the amount of hydrogen ion that is present in the solution, or it also can be referred to as a measure of acidity or even basicity of a particular solution. So generally, we have that pH equals to minus log of H plus, concentration of H plus. So to get the pH of any solution, you need the concentration of H plus that is present in that particular solution. So for any question given to you, the first thing to get or to determine is to determine the amount of H plus that will be present in that solution, whether it is an acid, whether it is a base, as much as it is an aqueous system. So you can determine the amount of H plus and then use the amount of H plus in molarity to determine the pH. But there is a way you can also get the pH from the concentration of the hydroxy ion. For example, if what you can tell us is about the concentration of the hydroxy ion that will be in a particular solution, you can also use that to determine the pH of that solution, because we also have that pOH, that is the pOH will be equal to minus log of concentration of OH minus. So you can use the concentration of OH minus in a solution to determine the pOH, and the relationship between the pOH and pH is given by pH plus pOH equals to 14. So in a way, if you know the amount of OH minus which you can use to determine the pOH, you can now use the pOH to determine the pH. By subtracting it from 14, you get the pH of that particular solution. So, and that's the relationship between the pOH at the same time the pH. So relating this expression, we can also say that the concentration of H plus multiplied by the concentration of OH minus equals to 10 raised to power minus 14. So the product of the concentration of these two ions will give us 10 raised to power minus 14. The idea about this comes from what I've talked about earlier, which is the fact that water can self-dissociate. Particularly when water dissociates, they give, like I said earlier, when water self-dissociates H2O, it produces H plus, and then we have OH minus. So when water dissociates, they produce H plus, which is hydrogen ion and hydroxy ion. But it has been determined that the product of the concentration of these two will always be 10 raised to power minus 14 at 25 degrees Celsius, and that's why we have. So this idea is from the ability of water to self-dissociate to give us to give us H plus and then to give us OH minus. So the idea is that you can either use all of these expressions I'm giving now, you can use it to calculate the pH. So in some questions, you might know the amount of OH minus. You can use this expression here to calculate the amount of H plus, and use the amount of H plus to calculate your pH. In some occasions, the focus might be to calculate the pH. So the same thing still apply. You can use, if you know the amount of OH minus, you can calculate your pH. or if you know the amount of H plus, you can use that to determine the what? The amount of OH minus, which can now be used to determine the pOH. And that's how that goes. And like I said, acid increases the amount of H plus in a solution, while base decreases the amount of H plus in a particular solution. Now, the next thing to talk about is that different acids and bases behave different way in a solution, and that is why we have what we call strong acid, strong base, and we also have weak acid, weak base. Now, the difference between the two is just the extent to which each of these substances dissociates. Strong acid or strong base dissociate completely in a particular solution, while weak acid and weak base dissociate partially in a particular solution. What that implies is that when you have a weak acid will not produce all, will not give us all the H plus it can produce. So it will partially dissociate. But a strong acid will produce all H plus that it can produce. So an example of that can be seen in HCl and acetic acid, CH3COOH. So for HCl is a strong acid. So when it dissociates in a way, it will give all its H plus, and then we also have Cl minus. So HCl as a strong acid gives all its H plus, but ethanoic acid, which is also the acetic acid, does not do that because it is a weak acid. So it will also produce CH3COO minus, and we have H plus. But in a way, in the case of this, not all the H plus that was supposed to be produced will be released from this particular substance. So if you have 0.5 mole of HCl, 0.5 mole of H plus will also be produced because a strong acid will dissociate completely. But in this particular case, for a weak acid, if you have 0.5 mole of this particular weak acid, not all the 0.5 will dissociate. So in a way, you can just have 0.1 H plus, which means that not all this substance dissociates to give the H plus, and that makes the difference between a weak acid and a strong acid. The same thing happens with a base. A strong base will also dissociate completely, and then while a weak base will not dissociate completely. So when dealing with a strong acid, all of these expressions apply because a strong acid will dissociate completely to give all the possible H plus. But when dealing with a weak acid, like I said, will not produce all its H plus. So, and that is why in determining the amount of H plus produced by a weak acid, we use what a parameter that we call Ka, which is dissociation constant of the acid. So Ka is only related to a weak acid or even a weak base. Although in terms of weak base, what we have is Kb, which is dissociation constant of the base. So Ka is just like a parameter that tells us about the extent to which a weak acid will dissociate. That's what Ka tells us about. At the same time, we also have another parameter that we call pKa. pKa is just in the same manner. So we have that pKa equals to minus log of Ka. But like I told you, Ka is just what tells us about, it tells us about the extent to which a particular weak acid can dissociate. But Kb, on the other hand, will tell us about the extent to which a weak base can dissociate. So anytime you are looking at a strong base or a strong acid, you don't need to consider Ka or Kb. But when you are looking at a weak acid or a weak base, you have to consider the Ka or the Kb of that weak acid or weak base, because a weak acid, like I said, or a weak base will not completely dissociate in an aqueous system. So they partially dissociate, or in another way, they don't release all possible H plus that they have. So, and like I told you, anytime you want to calculate pH of any solution or they give you any question, what should be your first focus is, how do I get the amount of H plus that I will have in this particular solution system. So, and that's the, so when you determine the amount of H plus or OH minus in that particular solution system, then you can use the amount, the concentration in molarity or in mole per dm to get the what, the pH or the pOH. At the same time, when you know one, you can use it to determine the what, the other one. So I talked about Kb, which is what we have for weak bases. So we can also have that pKb equals to minus log Kb. So I will do like two examples, one on strong acid and the other on a weak acid, just to give you an idea of what we are trying to talk about. Before I do that, I also want to say that for a weak acid or for a weak base, how do I determine the amount of H plus produced? Basically, to do that, you always have to write an expression for that particular weak acid. So in a way, I can have CH3COOH giving us CH3COO minus plus H plus. So in a way, let's say that they gave you a solution that is 0.1 molar and they said determine the pH. So what you need to do is that you have to do a kind of stoichiometry analysis in a way whereby you can say that initially you have 0.1 molar of this and this were not present. But because acetic acid is a weak acid, it will not dissociate completely. So we are not expecting that all this 0.1 acetic acid will also give 0.1 H plus. So we can just assume that let X be the amount that dissociates. So if X amount, if X mole of this particular acetic acid dissociates, that means X mole of this will be produced and X mole of this is produced. So this is determined from this balance reaction, because 1 mole of acetic acid will produce 1 mole of H plus. So if I have X mole of acetic acid dissociating, that means that X mole of acetyl will produce and X mole of H plus will be produced. So this is what happens during the reaction. So what is left, like after the reaction now, what we are, or after dissociation, what we are going to have, so what will remain, some of this particular reactant has been dissociated. So what will remain will be what, 0.1 minus X, and what you will have here will still be X, because some acetyl ion has been produced, and here you are also going to have X. So here you will do in a way subtract this from this, but here you will add. So and that's how we have it. So in a way you have plus, you have plus, because in reactions amount of product is increasing while amount of reactant is decreasing. So you can now relate these things that you have, you can relate it to the dissociation constant of the acid. So you can say that your Ka would be equals to the concentration of CH3COO minus, and we have H plus, over, then we have CH3COOH. So you can always do this. So in a way, anytime you want to determine the amount of H plus produced from a weak acid or a weak base, you have to consider the Ka. But when you are looking at a strong acid or a strong base, you don't need to do that consideration. So that is very important, because Ka or Kb does not apply to a strong acid. it only applies to either a weak acid or a weak base. So anytime they give you anytime they give you Ka or Kb, that implies that what they are giving you, the substance they are giving you, is either a weak acid or a weak base. So using this now, you can now say that means that this will now be the amount of H of this after reaction is X dot, we also have X over, then we have 0.1 minus X. Now if they are giving you the Ka, or even if they are giving you the pKa, from the pKa you can get the Ka. So you can now use the Ka and this expression to get this S, to get this unknown. This unknown will be the concentration of H plus produced from that particular weak acid, and that's how to go about a weak acid. So you cannot determine the amount of H plus from a weak acid directly without considering the dissociation constant of the either the weak acid or even the weak base, and this is how to go about that. But on a common ground, we always, there is a general, there is a general expression you can always use to determine the amount of H plus produced from either a weak acid or a weak base, but it always has a condition before you can use that expression, and that expression is given by this, that the concentration of H plus will be equals to the square root of Ka multiplied by the concentration of the acid, of the weak acid given to you. But you will only apply this if one, the Ka is less than 10 raised to power minus 3. Now when you have a weak acid with a Ka with a dissociation constant less than 10 raised to power minus 3, then you can apply this expression to get the amount of H plus which you are going to need to determine the pH. So we don't need to do this as much as the Ka is very small. In the same manner, you can also say that pOH minus for a weak base will be equals to square root of Kb, and we have constraint, but let it be that the Ka is very small and it is probably less than 10 raised to power minus 3. That's where this is applicable. But if this is not true, it's better to go through this particular way to get to get the amount of H plus produced for that weak acid or for that particular weak base. But let it be that anytime you note that the Ka is very small and it's less than 10 raised to power minus 3, you can simply just go through this. You can simply just use this without particularly writing all of these particular stoichiometry analysis. So for example, let's say you have a weak acid whose Ka is, let's say, 5.78 times 10 raised to power minus 4. Now if the Ka of an acid is 5.78 times 10 raised to power minus 4, in that particular case, since this is a value very less than 10 raised to power minus 3, you can just say that the amount of H plus produced from that particular weak acid will be equals to square root of the Ka, which is 5.78 times 10 raised to power minus 4. So let's say the concentration of that particular acid given to you, let's say they gave you 0.1 molar of that particular acid. So that means you are going to put 0.1 in this place, and then you calculate the amount of H plus produced. But you can only use, like I said, when the Ka is very less than 10 raised to power minus 3. But if that is not true, it's better to go with this, and that's how to do for either a weak acid or a weak base. But for a strong acid now, like I said, you don't need to bother yourself with Ka or Kb. So for a strong acid, we have that. So let's say we are given 0.1 molar HCl, and we are to determine the pH of this particular solution. So that means I'm going to, taking a strong acid in a way, a strong acid, like I said, we produce, in this case we have H plus and we have Cl minus. So because of that, so that means 0.1 molar of this will also produce 0.1 molar of H plus. So you just use your, so that means that the concentration of H plus here would also be equal to 0.1 molar. So and then you just use this concentration to get your what, your pH, and that's fine. But in a way, let's say probably you also have, let's say we have 0.1 of H2SO4. H2SO4, so it's a strong acid, so we have this giving us that will be 2H plus, and we have SO4 2 minus. So in this case, we have 0.1 of this particular acid. Now, because from the balance reaction, 1 mole of this produce 2 mole of this. That means this will be 0.2 H what? 0.2 molar. So the amount of H plus that produced from this place stoichiometrically will be what? Will be 2 times the amount of acid that you have. So 0.1 of this will produce 0.2 molar of this, and this will be the concentration of H plus you are going to use to determine the pH, since these two are what, are strong acid which dissociate completely. You don't need to apply Ka, and that's how to go about that. So basically, like I said in summary, to calculate the pH of any solution, determine the concentration of H plus in mole per BMQ present in that particular solution, and use that to determine the pH from the expressions I have given unto you. Although in some cases they can also give you reactions that involve acid and base, whereby you have a solution that involve acid and a base, and they are asking you to determine the pH of the resulting solution. It's fine. The same thing still applies. Determine the amount of H plus. I told you from the beginning that an acid will produce H plus, while a base will remove H plus. So if you have a solution that contains both acid and a base, so what you just have to do is that you calculate the amount of H plus that will be produced from that acid, you calculate the amount of H plus that will be removed by that particular base. So the amount of H plus produced minus the amount of H plus removed by the base. So that will give you the net H plus that will be present in that solution. And you can now use that to determine the pH of the resulting solution. Although in some particular acid-base reactions, the salt form can hydrolyze in some cases, especially when you have a strong acid with a weak base, or when you have a weak base with a strong acid. So the resulting salt that is produced can hydrolyze, and also that could affect what's it called now, that could affect pH. But let me just not talk about that. But just know that anytime, the major thing in getting the pH of any solution when it involves reaction between base and acid is, first, know the amount of H plus produced from the acid. This is the amount of H plus that the base will remove. So what is left, the question now is, what is the amount of H plus left in the solution? And that will be the amount of H plus to determine the pH of that particular solution. So I hope in this particular class you have learned one or two things.